Hey everyone, I'm gonna get started with the carding stuff. So I have some quick announcements. Back to our Slack channel, project. All of us online or here in class will need to secure we're associated with the project. So instead of say, post your slides like the other things have already done. The project channel. You can hit it or something like that. Pin the other, and then you add multiple little plugins. So I know that because they want. Then what I will do is I'll spend some time probably multitasking on the project. Anyone is welcome to make comments on anyone else's project. That's the whole point of putting Slack. Right? You get comments on that. And then subsequently, when you go to do your second spin, each later, right? What you would do is post reply is the same thread. And then at the top thread, you just react to. So that there'll be a 1 and a 2. Right? So every time we do that, all your information about the comments will be on the same thread. Okay. Or better yet, using something from slides or 365 PowerPoint. You can make let other people make comments directly on this topic, right? So that means I will go to your slide and make comments on your slide, so they won't other on. Either way is fine. I tend to use full slides a lot in script on slides twice because then it is one-to-one aligned with the point that you're trying to. That's an easy thing. Actually highlight specific text on the question, but that's not. So that's my preferred way of working with my students, and I'm extending that to how we're making project. Okay, so remember that put your slide deck, initial slide deck on projects, then in it, react with one. Okay, and then before the next sprint, you can take comments, and you can also at me and say, Ben, you haven't made any comments. That's not mean there's nothing new or I really need trouble or whatever. And I'll try to think about it. Okay. So I think we have today's Kahoot first. So that's half our Ben. Your name again? Erwin. Erwin is going to do Kahoot first. Then wait to see what. So please join the game. So that's you remember what happened last week. I think someone can you click on the QR code and do it? Okay, great. Very fun. Yeah,
Let's start. Especially is not keep on I should they find something that for achieving a very question which technique involves generating multiple outputs using a majority program. So yes, self-consistency. Both discuss consistency and fear of thoughts the small lines. So fear of thought and the small steps. But self-consistency lies on the majority input to get a consistent answer. What does Q on top? English. One, four, go from
volume on the mic down. Go ahead, give that down. Cool. Can you guys hear online?
Yes, Prof, we can hear.
Okay. Yeah, so when you're narrating, you guys hear online, then you have to do yes, Prof. Okay. Yeah, so when you're narrating, you guys hear online, then you have to okay. Yeah, so when you're narrating, you guys
the next question. What is form sensitive? So here's the first version of the the first thing on the effect that I want to some changes since the movement last but That's not set down. I think that's all the solution. Hopefully,
Also, thank Erwin for his series. Highly. Alright, very well done. So we're on to our lecture segment. Who's lecturing today? The first one is Erwin. This is fun. Yeah. Okay, online.
Hello, I'm here. Yeah.
Okay. We're going to let you share screen, right?
Yes, yes. Let me share. Okay. So it's visible?
Yes.
Okay. Thank you. Okay, so okay, yeah, let me go to the first. Okay. Okay, let's start from here. So hello everyone. So I'm Barid from WING Group. So in this lecture, we are going to talk about vector stores. So we believe vector store is an important component for our RAG model because we want to retrieve some additional like external knowledge and some verified information from some reliable resources. So in this case, we believe vector stores are a good component for our RAG. So in my section, so I'm going to give you some like a background of this technique, and hopefully you can get the motivation and the general idea of this component and this. Okay. Well.
Your slide. Can you try resharing again?
Okay. Is that okay now?
Not yet.
Okay, loading.
Sometimes it does take a couple tries.
Oh, our slides. We have so many slides. I guess it's quite slow. I guess.
Yeah.
Is it okay now?
You just saw something. I'm gonna try it again.
Okay. Now it's visible.
Yeah, but I think the slideshow is not working.
Yeah, if the slideshow doesn't work, you can just use the Slideshorter.
Okay, I see.
Fine. You just share the regular screen on Slideshare.
Okay. Okay. So I guess I only have 10 minutes, so I wasted lots of time. So yeah, let's start. So yeah. So in last few weeks, so we have discussed so many stuff of larger models, and we see larger models suffer from several fundamental bottlenecks and problems. So for example, so we see hallucinations from larger models, and to mitigate this and address all the problems, and we believe RAG is a good solution here. So so actually, so we see some like earlier expressions for RAG-like systems. So for example, so if you go to if you may heard the IBM Watson model. So actually, it was proposed like 15 years ago, and this model is based on is designed to answer some questions based on database, and also we have some other prototypes of RAG. So for example, here's my favorite one, so called Ask Me Anything from Stanford, and they also both frameworks use external database to support NLP models. But here's are some problems of this combination with the framework, because all of them are using traditional data stores. So they have to retrieve data, the information based on some kind of keywords searching engines. So for example, you can leverage stream matching algorithms to find all the relevant data. But a simple idea here is how about we just use this traditional data stores for our RAG system or our RAG framework? So answer is yes, we can do this, but we still see some limitations. So for example, in our RAG model, sometimes we want the model to support images, videos, and some other all kind of inputs. So in this case, traditional data stores we see some problems from these traditional data stores. So because all these models are designed to manage and warehouse stream data, and another limitations here is so when we try to search something, so some words have multiple meanings. So for example, if we want to search for mouse, so actually mouse has so many meanings. So if in that case, we cannot just use a stream matching algorithms to find all the meanings for this keyword. So since the BERT times, we have seen all kinds of data can be contextualized and vectorized. So a simple idea here is how about we vectorize, vectorizing all kinds of data, and then we try to build a vector store to manage and warehouse them for our RAG model. So a simple idea here is a simple solution. I guess it's a universal for all kind of RAG model. And then, so the following question is why we need such kind of vector source. So here's I think an intuitive example here. So when we are trying to search some relevant information for mouse, so as if we can just you leverage some similarity matrix to find all the labeling vectors for mouse, and we can find all the relevant information for mouse. And in that case, so I guess you can see it's very hard to use some stream matching algorithms to find some pairs. So for example here, so you cannot just try to match the scripts between mouse and Mickey. So this is, I guess, our motivations. So so we can use a vector stores to support semantic search and try to retrieve all the relevant information beyond the script. So here's some summaries of the advantages of the vector source for RAG framework. So obviously it supports unstructured model data, and also it can handle semantics search results. So as you can see in the example, and also we have seen some other advantages, we can use the vector stores to manage memories, and we can also use it to manage the caches. And we also have some challenges. Definitely, every model, every framework, every solution has some challenges. So you will see in the same examples. So we see when we trying to retrieve some relevant informations from the vector stores, we'll also get some some noisy data, and also get some some less relevant information. For example, here, so we retrieve some information about the giants. So invalid reverse, so a mouse is a giant. So, and also have some challenges in vector storage. And so in this lecture, so I guess my team will discuss lots of things about vector stores, and we are trying to solve the challenges mentioned here. So hopefully, so you can get everything about the vector stores, and can you help to your RAG system. So okay, so that's it. So any quick question? Yeah. So any quick question? So yes.
Anyone online would like to ask Barid a question as well? Okay, I mean, it is the first part, so you guys are getting warmed up, so I hope, again, you make a point to, especially for those of you who are more senior or doing it more time, in other words, CP, if you want to wait do select one section of the lecture to pay close attention to and make a comment or ask a question that's really way to make the learning experience. Great, thanks, Barid. So we'll move on to our next presenter, Benn. Frederick. So again, go ahead. Sure. Whoever is delegated to structured catalyst can also help put up some questions on the general channel.
Can I ask a question?
Yeah.
Regarding vector thousand, how do you actually train embedding model?
Sorry, I can't hear you. So
Okay, let me speak about how do you train an embedding model?
so I can't hear you clear. So do you mean so how we can train a vector model or retrieval model, right?
Vector embedding model. How do you train that model? A vector.
So actually you have several ways to train embedding models or a vector store model. So for example, you can use BERT, or you can simply use some like a classic word vector like algorithms. So in my case, in my example, so you say the mouse example. So and all the vectors are trained by the word-to-vec algorithm. So I guess so, and so it's about like a vector storage like a challenge. So and we also have some like challenge problems here about the information capacity of the vectors. I guess my team will go through all these challenges, and hopefully they can also help you understand this problem. So does it make sense? My answer, yeah.
I think that's fine. I mean, there are lots of papers that are sort of like a prerequisite to learning how to create embeddings. The word-to-vec is probably the easiest one to start with. But there are many other models that will be that. That will help you at least run the code for making an embedding and understand the math behind it. Yeah, but those are things. Yeah, you can sort of take for granted as a black so you pick it up. But if you want to get more clear understanding, you can take an NLP class, have a lecture specifically on word-to-vec, that goes over that and exactly how to do that. There are plenty of courses online that go through this. That's a great question. Okay, so over to Frederick. Okay, can you guys on remote see the screen? Because we had some problems with screen share earlier. Yes, okay, so they can see it, sorry. I know if you go this slideshare mode and so you can move the bar out of the way too.
Good evening, everyone. Yeah, what about vector storage techniques? first of all, the question arises, why do we even vector storage techniques? Or more specifically, why do we find a way of storing vectors and giving those vectors very fast? The answer is quite simple, to be honest, because RAG especially relies on retrieving embeddings from huge data sets to provide very information. So because of that, we would need certain techniques because we can't always query or use certain normal search algorithms for RAG especially when we have the high dimension. We want to want to make the whole process more efficient. So I'll be going over some of the storage techniques. First I would categorize them as where we have a first technique called hierarchical navigable small code. It sounds like a lot, but I feel like all algorithms and techniques can be analogous to day-to-day scenarios. This was the intuition behind hierarchical navigable small code, which is basically like a multi-level signal. So let's say if you want to find a certain house or an event that's going on, you will first see a zoned out map, similar to using Google Maps. Okay, where is this certain event in, let's say Canada? Then you would go in Canada and search for a specific area, Quebec. Then you would go in Quebec and search for a specific street, and then you would take a house. This is the same analogy that's used in hierarchical navigable small code or HNSW. And fun fact, MongoDB in 2019 shifted the whole vector storage algorithm for the basic queries to HNS. The whole algorithm is pretty, the idea is same as the analogy, so the whole algorithm is pretty complicated, I would say. But you basically have one algorithm for insertion layer, one for a search layer, and third is your select neighbors to the state, which is also a special algorithm. First, the paper mentions that algorithm 4 is only used for select. This algorithm especially will be gone through much detail in the coming slides by my other presenters. So I would just jump up what are the advantages and disadvantages of this algorithm. It was first presented in the paper 2016 by Markov and Yisong. But the algorithm includes logarithmic time complexity, so O of log n for user queries, and also achieves high recall, and it's very scalable. To be honest, it's way better and outperforms most of your other algorithms like IBM or LSH. But there's coming with a lot of advantages, there's also disadvantages, which means the main disadvantage is high memory usage because it takes a lot of data, a lot of space in general, like 1 to 2 GBs per million vectors for storing the whole graph structure, which also means that it's very CPU intensive and to create the graph in general, it's very slow. Yeah, that's pretty much what you need to know about hierarchical navigable or HNS. I think from my segment of the lecture, this probably is the most important algorithm you should know. Moving on, we have something called inverted file or IVF. IVF is especially paired with another algorithm called product optimization. So product quantization of we should be talking about more later. But its main intuition behind IVF is also similar to HNSW, but since it came before HNSW, because first the analogy is if you go into a library, you would, let's say you want to pick a book, so you would go section by section, maybe mystery or maybe sci-fi, history, fiction. And then you would go to the section and pick a certain book. So let's say if you want a book that is like fiction, but still has a bit of history into it. So you would be like, okay, what if I go to the center of these two areas? Then I would find a book that is related to history and fiction. That's the whole idea behind inverted file algorithm. In this case, instead of you going to a certain area or a book section, we use something called centroids to determine which area we need to check. So, and then you would query the nearest vectors in that centroid. And yeah, as mentioned, this strategy drastically cuts down time there. But then again, HNSW does beat IBM. To go into more deep about the algorithm, how it works is it uses something called approximate nearest neighbor ANN. Technically, all of the algorithms we'll be discussing are a version of ANN algorithms in general, but this one partitions vectors into clusters using something called a force quantizer. Fancy terms, but basically what you're doing is you're trying to split your vectors in different form of clusters based on a certain equation, which is your force quantizer. And you don't know how many clusters you want to separate it. So that's where your case endpoints come in. Then you can form an inverted index where each centroid maps to a list of vectors. But as I said before, this algorithm is always paired with product quantization, which I'll talk about later. Offer integrated product quantization, and this is a fancy way to normalize variance across your vectors. But at the end of the day, IVF is still a very popular algorithm. If you want like something which is more precise, and it also beats HNSW in terms of memory because it consumes less memory than HNSW. Moving on, we have something called the next algorithm, which is called locality sensitive hashing. Again, fancy word, but the algorithm is very simple. To be honest, this is probably one of the algorithms which I love reading the whole paper about because it goes on to the principle that given a certain hash function, there's a higher probability for your hashes to end up in similar groups by itself who's your hash function to be correct. As I mentioned here, that to find items similar to your shopping list, you don't visit every store. Instead, you use a clever system where goods are grouped into baskets based on shared rates determined by quick potential. And yeah, the image should show what I'm trying to convey here. Basically, if you have a group of elements and you want to separate them or split them onto a hash table, LSH makes sure that each group of each group of the table has some form of similar trait, which it then exploits to sort of like query and retrieve data way faster. Yeah, the last line explains it pretty much clearly, allowing you to scan only a fraction of the data set in queries. Go into a bit more detail, as I mentioned, since all algorithms are some or other way of ANN algorithms or approximate nearest neighbor search. LSH uses ASS or approximate similarity search in high dimensional spaces to approximate nearest neighbor. As I mentioned again, it uses core idea is to use a family of hash functions that are locally sensitive, meaning the probability of collision decreases at a distance between point. Basically, similar traits. It also addresses the curse of dimensionality, where exact neighbor search becomes impractical. What's the curse of dimensionality? The curse of dimensionality, TLDR, is as if you keep on increasing dimensions, your function is going to get sort of overfitted in a sense. So because of which your query retrieval is bad. I mean, yeah, it's quite bad. Other than that, in terms of time complexity, you have your peak velocity, time complexity. But the base time complexity depends on the number of points, the number of hash tables, the number of candidates you want. Yeah, that's pretty much what we know for locality sensitive hashing. So, and LSH. These are the three main indexing algorithms: HNSW, IVF, and LSH. Why I keep on repeating is they are pretty important algorithms, even outside of this of today's section. You can find them almost everywhere in use in real world applications. This is a quick summary. You can look into it. Okay, besides later. Moving on, quantization techniques. Quantization techniques are also confused with dimensionality reduction techniques. But quantization techniques only compress vectors to reduce storage. They don't actually reduce dimensions. Because for RAG in general, we don't want to reduce dimensions. Moving on to the first quantization, which is probably the most confusing, but the most cool quantization technique. It's called product quantization. Product quantization, which my fellow presenters will talk more in detail as well. But in general, product quantization uses the analogy that, let's say if you want to remember a bunch of faces, instead of just going and remembering each face, what you do is you split the faces in sort of like this face as you split the faces into small parts called, let's say, faces, eyes, nose, mouth, and so on. And when you want to search something, you use the specific small parts to search rather than uh, the whole face, which is way faster and also saves a lot of space. In this case, you each category, let's say for face, will have a PQ code or product quantization code. That's what is being used to search these faces faster. Let's talk more. By right, product quantization enhances vector compression by compressing high dimensional spaces into lower dimensional subspaces. Basically, high dimensional subspaces into lower dimensional subspaces. Using the face analogy is your face will be of a higher dimension because it encompasses multiple different vectors like your eyes, your nose, mouth, and so on. So what it does is it splits them into lower dimensional subspaces and then forms a large code book. Code book is your product quantization codes. Then for each subspace, dedicated code book is learned from k-means clustering. You use a normal clustering algorithm. In general, you could probably use any clustering algorithm or any algorithm. Right? But yeah, that's pretty much the idea behind product quantization. I'm sorry. Yeah.
How do you do more? How do you do? Oh, the break. It's a break part.
How do I break? Oh, okay, sure. So for product quantization, let's go back to this diagram, which should explain and use the diagram as so this is your original vector. It could be your n dimensional vector. In this case, let's say it's an hn dimensional vector. Then you would break it down to smaller subvectors, which will be of a lower dimension. So call them LP. That's why the analogy of your face comes into place. So you have your face, your original vector, your eyes, nose, mouth, any other parts are your subvectors. Then
Yeah, I didn't interrupt you, but so my question is if you concat these vectors, right? Is it like original vector? So it's not
correct.
Oh,
Yeah. So you can use the subvectors to build the load.
So is like some actually cut or I mean I understand I'm not there. How exactly break? Is there any based on some features or based on some artificial
Oh,
fixed lengths or
correct. You can hold on to it because it's explained later.
Okay, thank you.
I'm just summarizing that all the then got it. But it's a very good question. Actually, the whole process itself is very interesting. Because there's a bunch of ways you can get it done. And the more I read about it, the more I was like, the math just gets crazy. So yeah, it's coming this. So sorry I couldn't answer.
So TLDR, you can do it many different ways. You can assume that the vector has the information uniformly spread out. So any way you cut up the vector, it is somewhat representative. It's a lower fidelity version than higher. But like Frederick says, there are many ways that you may try to group or cluster information so that there is this semantic idea of face, eyes, intercomponents, right? So
Moving on, then we have scalar quantization, which is not used as much, but it's still an algorithm. Like you just convert your original vector to a sort of like a smaller dimension A vector. So in this case, we are converting from 32 dimensions, 8 dimensions. That's pretty much what we need to know about scalar quantization. Binary quantization also works the same way, but instead of lowering it down to like any n dimension, you lower it down to just ones or zeros. Yeah, that's pretty much what we need to know about product quantization, scalar quantization, and binary advantages. These are the advantages and disadvantages. And moving on, we also have certain famous algorithms for vector retrieval. This one is technically not covered, but it's just for information because these are like, this one was created by Spotify, by the way. These are pretty interesting algorithms. Anna uses something called random projection tree. I'll just quickly explain what random projection tree is. The whole idea of random projection tree is to randomly take a vector and use that vector to split the given data set. So let's say because we're dealing with a huge vector space. So randomly take a vector and use that to split vectors on based on that hyperplane. Then you keep on doing it till you reach a certain like A or M, whatever is right. And then you use these hyperplanes to then query and retrieve the vector from. That's approximate errors versus or annoying. You also have Bamana algorithm, which again we talk more in detail later. Is similar to your road networks in general, but the thing is, after you construct your whole graph, you would then run a pruning layer where cuts out right, where it prioritizes different types of edges based on your event data set. Again, the pruning process is dependent on this alpha factor. Sorry. But yeah, that's pretty much it for this algorithm as well. Here are its advantages and disadvantages. These are my remarks. So thank you so much.
Okay, so Hongi, are you in the room?
Hi.
Yeah, okay. So if you go to the general channel, there's some discussion by a couple of people. Yeah, Indra is, I think, putting things on as the discussion catalyst. And if you posted your slides for projects, I'll be slowly. Okay, over to you.
Thank you. Okay, hi everyone. I'm Hongki. I'm a year 2 engineering student. So I'll be mostly lecturing on product quantization and a few techniques. So just a recap. So just now Fred has mentioned about the different like nearest neighbor search. This is really optimal for RAG-based or high dimensional vector embeddings. So usually what we're using is ANN. So out of the many approaches, my focus is mainly on
Yeah, good. Or to get the application. It's on the bottom.
it's mostly on just product quantization and working on like these parts. So okay,
You guys see the annotation? Yeah, okay.
okay.
Yeah. On the go back.
Okay. So to introduce the problem of retrieval, so we have a few problems. First, you must make it accurate, efficient, scalable, and of course, flexibility and resource use are also a plus. So the main problem that we're dealing with here is that information in high dimensional spaces are very sparse. So like a lot of it is just kind of nothing. So this means that it's very easy to just exponentially grow your size of your database, and to retrieve this is very difficult. So these are some trade-offs that we should consider. So I'll just start off with quantization. So basically, know how I said that data is very sparse. So usually this means like what? In some high dimensional space. And Fred has mentioned that it's good to divide this space into many like subspaces in which we have like in here we have here we have different like smaller regions which exist within our space of our high dimensional space. But then to actually solve for these spaces and build a good representation of our vector database is very difficult because of the high dimensionality. The problem is, I think, to solve for these like code words, which you can think of keys for our vectors. Even though it's an NP-hard problem, and it's just basically impossible to solve in any reasonable time. So what does it mean to do
to solve using a quantization approach. So basically to start, we build a code book. So what exactly is a code book? We usually cluster the vector space with k-means to get representative centroids. So what are centroids? Centroids are this stuff. These small points kind of represent a cluster of words, or maybe it can be some sort of semantic meaning. And when we want to add a vector, we kind of index it, and then it is like assigned to a centroid. So sort of you can think of it sort of like a hash. So when you hash it, this thing is its key, and you pull out whatever's inside this Brony region. So I guess this is like the boundaries of what vectors you get hashed to what spaces. But the main issue with such an approach is that it's very difficult to actually implement with, for rec, because you're trying to index a lot of information. Like imagine you're putting your Facebook and you're trying to index people's posts or like your ex, and then you're trying to put in tweets or whatever. So yeah.
A little bit basic question. So K means actually the K is actually the type of permission.
Yes.
How to access?
Okay.
That's very basic. Sorry.
Yeah.
You may not have answered.
We'll get to that later. So it's more about the implementation itself. So, oh sorry, I should have gone this earlier. So yeah, this is a very difficult problem. The dimensional space is very large, and yeah, it's very sparse. So just now how we defined a lot of these subspaces that have like many different colors. The main problem here is that we notice experimentally that the more subspaces we have, the better our retrieval is, and I guess the more granular we can have each subspace to be. So yeah. So in practice, you get less distortion. Don't need to worry about the M's and moment yet. So this. So just like how Fred said, for example, we have a large vector that is like very long, like an n-dimensional vector. What we do is we basically just chop this up into many sub-vectors, and I guess as Prof said, they kind of relationships, and we pray that they kind of work. And at the same time, instead of quantizing this entire thing and doing k-means across like a few thousand dimensions, which is not computationally feasible, what we do is, especially for large K, right? Large K, yeah, we define many subspaces, very difficult. So we kind of break the problem down. We do these subvectors, and then we quantize. We quantize them, then we apply our hashing function. So okay, so you can imagine that we divide it into an m amount of like different smaller vectors, and then we apply our quantization. So how does this look like in practice? So basically, after we quantize into these smaller spaces, we basically get a total. We are able to represent a larger amount of codes with less computational requirements. So we realize that we can actually store an exponential amount of code, in a non-exponential amount of we have an effective gain in amount of codes with a less gain in amount of centroids. So we realize that what we see just now is the distortion error. This is actually this image on the right kind of shows us the kind of error that you're bound to. So
If we go back. So are you guys getting the efficiency gain that Hongyi is saying for us here? The two equations down there, right? Effective total code is to the m power, right? Because you're doing the product at the top, right? But because you cut it down into smaller parts, you're quantizing each part, and there's redundancies in the code, right? Like you have a code in I1 in the first text. That also happens here in I2. But because you quantize it the same way, you have to only store the copy once. Right? So then you get the cost savings that he's put on the bottom of the page, right? You're storing much less information because your code books are served over multiple sections. Okay, so yeah, Agit.
So now the centers are the ones that store the information about the vectors.
Yeah, so if you can think like you have a three-dimensional vector, right? Okay, so it has scalars in three dimensions, right? And you want to quantize that. What he's doing is something like, okay, I'm going to treat each of the projections x, y, and z separately, right? Okay, so if I only have a one-dimensional vector, and instead of allowing like 7 decimal places of precision, I only allow 2 or 3, right? Then I'm losing some precision on that. But aggregated together, they can reproduce the original vector with some loss, but it will take less representations because the amount of code that you have all only 2 digits or 3 digits. That makes sense. Okay, because if you took the 7, let's say you took the 3-dimensional vector and you quantized it with the same amount, but because you're doing a 3-dimensional vector, you chop it, it will still have a lot more digits of precision. So your code book would be much larger. That makes sense. So that's the cost savings that you're getting from dividing up and then saying for each dimension or for each subset, right? I'm going to quantize that separately and then compose together. I can build back the same product. Of course, it has some loss, but you're really getting a lot of compression. So I like to think of it as taking, let's say, a 3-dimensional vector instead of compressing the 3-dimensional vector by quantizing the whole thing. You quantize each dimension separately. Go ahead. Okay, sure. So, everyone, do you guys know what the Voronoi cells are coming from? Everyone here is familiar with K nearest neighbors. I see lots of nods. Anyone doesn't know? Fine if you don't know. Then somebody else who knows can explain it. Okay, so
I think like Voronoi cells arise when you try and find the equal distance between like each centroid. So.
Exactly. So it's a side effect of the centroids having the least perpendicular distance between 2 centers finds the dividing line between each cell. Right? Perfect.
Okay. So this is, I guess, that was the main idea behind PQ, the optimization, and that it allows you to actually store a lot of different codes without incurring the high cost of compute. So okay, so to the paper itself, on the original PQ paper, they actually introduced this thing called IVFADC, which is not only just the PQ optimization, but as well as the inverted the IVF that just now Fred actually mentioned about. So so in practice, what they actually do is in the paper, they not only did they use PQ, they also use a cost quantizer. So imagine at the start, instead of doing a very like well and very, I guess, distributed codebook. They just kind of did a simple one, which is like 1K to 5K clusters, and they basically just use this as a router. So after they do this, then they run the PQ optimization. So the exact optimization they're running on isn't exactly on the full vector, but actually just on this thing called the residual vector. So what this actually means is they don't break up the entire vector, but instead they just kind of get the distance between the centroid or the vector between the centroid and the vector that they're querying for. So the hope is that this allows for even more fine detail and more like, I guess, it kind of distributes the data better so that the centroids are just formed slightly better. So just like so let's say in retrieval time, you make a query, it will come in, it will be it comes in and it gets broke. It first gets routed to the correct database per se. Then after that, then you run the PQ. So this kind of you run the PQ, you break it up, and you route it again to the most fine level of detail / semantics. Okay, so the last one I would like to introduce is this paper called which is the Facebook AI similarity search. So this is basically like, I guess, the most practical way of implementing PQ at the moment, and it's actually almost the same method as the original PQ paper. But the one issue with the PQ paper was that it was not parallelizable, right? It was not easily parallelizable. So like you cannot put through the entire I don't know how many tweets that comes out in a day into the database. And what they are doing here is they implemented a few algos with the help of, I guess, CUDA and a bunch of parallelization optimization such that now it's actually feasible to put it on a real server and real hardware. And I think they have open sourced the entire repo, so I think that might be of good use, especially for projects working on quantization. Yeah. I'm not gonna pretend I understand how the CUDA works. So I think that's all I have for my part. Thank you very much.
I have a comment. So, like, I'm no expert at CUDA, but like to the last point that you said, what I know is that CUDA naturally like works in terms of the hardware is like a lot of cells, right? That are like essentially like rectangular blocks. So like my hypothesis is that because quantization involves like breaking things like regular blocks, that makes it very easy to put them into the individual cells in a GPU and then run the computation. Yeah, I don't know. Maybe
That makes sense.
Yeah. Yeah, parallelization is a very big savings, right? That you can get from doing things at lower constellations. And you can do it distributedly too, right? Which means if you have a data center in different places, you can arm the work off to the data centers and have each part of the system, one part. That's a really big part of the niceness of the tensor map, right? Because you have this big, ugly, n-dimensional tensor, you can chop it up in different ways, you can hand it to different servers to do things. So I think one of the good things that Hong Yi presented was the residuals, right? So you have the case of quantization doing the coarse grain, right, which is at a high level. And again, here, just like Indra was just saying, the important thing is coarse grain means what you have a lot of fidelity loss, but it also means because it's coarse, it can be done very quickly, right? That's the essential thing that like we learned from Google and other information technology. Things can be very fast, they can be distributed, they can be very good approximation. You can do this over and over again. Like you can have a coarse grain approximation to another coarse grain approximation to another coarse grain approximation. But of course, then you have more computation. Right? Those are some techniques. But then the second part of that part was that to do the residual calculation, right? So where else do we see residuals? Anyone tell me? We have it not so much as in gradient descent, but there's another very famous architecture that has residuals. Attention and transformer blocks, right? So we have residuals in other places because basically a transformer layer is trying to capture as much of the signal as it can in that layer, but it's just passing on the buck and saying, well, this part I can encode, you guys deal with it downstream, right? So it's basically passing that on as a part. So the residual allows you to model things well, right? And of course, approximation is allowing you to model things fast, right? So the fast is important, but if you haven't gotten it completely right, like Hong Yi's slide says, the residual you model so that you can get fine grained correction, right? So it's like going to the library and then trying to use the Dewey Decimal System to find a particular book, right? You look at the 600s, then at the 610s, and then down to the decimals for that, right? The residual is sometimes telling you, oh, you went to the wrong shelf, actually, in the other part of the system.
One more comment. I think just now somebody asked about how will we decide on how to break up the vector into like in practice, like how many M's do you want? So honestly I think that's mostly based on, at least on the paper, they did do like evals for different M's. So like that's different points you see on the line. And I guess they provide different levels of granularity at data set.
Still like a hypergram.
Yeah, it's like a hypergram. Most people just empirically do that. There's probably some type of empirical scaling law that you can probably derive. But yeah, in practice, most people just try it out.
Thanks, Hong Yi. So I think Hong Yi gave a few more quantization of investigate error tables. So now I'll be talking more about graph-based approach, and SW approach. And I think the best way to explain this is to use like the data structure that all of us are really familiar with, right? So the idea of the H and SW is actually borrowed for the idea of skip list. So what I have over here is a skip list. So a skip list is a probabilistic data structure that actually allows us to search in block at time. And I'll actually use the intuition on a skip list to actually explain about H and SW. So just a quick overview of like what a skip list is. So it's basically, you can think of it as a linked list, right? You can think of it as like a linked list at the bottom layer. So at the layer, this is like your usual linked list. Then the thing is that why is a linked list slow? A linked list is slow because we need to traverse through like n nodes before we get to our destination node. So how can we improve the time complexity of a linked list? We can do this by using this notion of what we call express lanes. So express lanes are established like the upper layers. So like over here. So this is what allows us to skip forward a few steps. So it allows us to keep skipping until we find like our destination node. So in this case, if let's say we are trying to search for, let's say, like 17. So we'll start from this node, we'll jump to 7, and then over here we'll check, oh, 29 is greater than 17. And if 29 is greater than 17, then we go back and then we start to continue to traverse the second layer until we find like the first element that, like the largest element that is lesser than the value that we're searching for. And this is eventually how we repeat this process across like multiple layers until we converge on this point. This is how we find like the insertion point of like 7.
yeah, so this is the idea. We just easily go as far right as we can, and once we can't go right anymore, down. Yeah, so this is essentially what I've previously demonstrated. So now if let's say we want to like delete like a certain value, what we do is that again invoke the search operation. So again we try to search for B and then we delete B from all levels that it participates in. So if let's say we want to let's say like remove let's say like we want to remove like the element 16, we will search for 16 using like the search function that we defined earlier, then we will remove 16 from all levels, from level 4 and level 3. Cool. So what is the time complexity of skip list? So in the highest level, right? So in the topmost level, we will see like because there's approximately we can skip approximately n over 2 elements. So this means that we can always cover like we can cover like half the length of the linked list in the first highest level, and then as we go down on like lower levels, we can actually skip lesser and lesser. So in like the second highest level, you can skip over n over 4 elements. In the third highest level, you can skip over n over 8 elements. So this means that the height of the skip list, right? So the number of the levels in skip list is actually bounded by a log n. So essentially, intuitively, this will need to like we need like log n hops in total to find an element. So following like the inclusion from the skip list into like the HNSW graph construction, what we do is something similar. So in our base layer, right, in our bottommost layer, we have all of the vectors, right? So this will form like our base layer. Then as we go up, right, as we go up in like the second bottommost layer, we will take like a few vectors and put it on like the second bottommost layer. And then we repeat this until like we form like the entire HNSW graph. Yeah.
Oh, I think this explanation is very intuitive. Two questions here. If you look at the graph, you know, the system graph, how do you form this one first? And how do you form this one? Oh, and how do you assign the value? Because you are basically jamming by the value. Navigation. So how do you construct this?
And like we graph in the base layer.
I mean, construct this.
Oh, like the skip list.
Yeah.
Oh, I think from my understanding, like the initialization of a skip list, I think let's say if we're given like some array of integers, what we do is that we go through every element in the array, and then for every element I in the array, we initialize like a linked list node, and then we set and then we just keep traversing, and then we set like the next pointer of the current node to point to the next element, and then we set that. I think that's how I would. I'm not sure actually how implemented, but that's how I would.
Other levels random.
I don't think it's random. I think it's. I think it's like I think it's based on like the height of the linked list node. So if let's say like we denote this at level 0, level 1, level 3, I think let's say at this level we would try to chop at like half at like the midpoint, and then let's say at this level we will try to chop like half of the midpoint of the midpoint, like 1/4. So this ensures that we can upper bound like the number of elements we can skip at every level. Yeah, so I don't think it's randomized, but I think there are some implementations that are.
Just now you went through like the insert function, right? Like maybe like initialization is just a list of inserts.
Yeah.
Yeah.
Oh yeah, possible. Yeah.
Well, a lot of the algorithm too, we actually cover in the CS305. I mean, this I'm pretty sure we did. So you might want to review it actually if you're taking courses at first level later on. So these as just what is implied here is it's a logarithmic, right? So logarithmic means you're usually doing some base 2 type of manipulation. So it's exactly like what Ben is saying. So cut it into half and do it halfway, right? You can also do this not with linked list, you can also do this with an array. So you can think how could you do it with an array data structure and jump, powers of 2 down in elements until you reach place which exceeds the key number that you're looking for, and then reverse the decision. Okay. A lot of these algorithms work really nicely when the data is static. Okay. So you can make a very nice skip list that has exactly n over 2, n over 4, etc. when things are static. What a lot of people care about is when the list is dynamic, right? Because in a lot of data structures for IR, you care about when documents get deleted or documents get inserted. You can think about Spotlight on your laptop, right? It like heats up your laptop when it's trying to reindex, right? So it does all of this thing, but it has to dynamically outdate things that aren't in the system anymore. So if mark something is deleted rather than getting rid of it. Okay, and then insert new nodes. Okay, so those are 2 operations that happen. Sometimes when we do deletion, we do exactly what Ben says, which is we actually delete the data structure. But many times, we don't actually do that. It's actually faster to mark something as deleted instead of removing it and fixing the data structure. Right. So occasionally, Spotlight will reindex, right? And this says all those deleted flags. I'm going to update them. I'm going to make this beautiful n over 2, n over 2, n over 2 linked list from scratch all over.
So essentially the same logic, like the same can be carried over as to how we can construct this agent as our graph, the variable, navigatable small world graph. So we have like the most number of vectors in the outermost layer, and then number of vectors that every layer decreases as we set up graph. Yeah. So in terms of like HNS traversal, so like how, so even like a query vector, right? How do we find the nearest neighbor, right? So that's the problem that we're trying to solve. We're trying to solve the ANN problem, approximate nearest neighbor problem. Given some query vector, how can we potentially find the nearest neighbor to this given vector, right? So, I think the approach that was suggested was that we can actually greedily choose the neighbor that will keep getting us closer. So I think it's something similar to Slideshorter in a sense, where we just keep greedily choosing like the nearest neighbor until we can't get any more closer to the query vector. Yeah. So in terms of like the layer hierarchy, so what we do is that we first start from entry point at let's say like the topmost layer, and then we see if there's any neighbor that is near like the query vector. And then if there's no nearest neighbor, then we continue to descend to a layer below it. And then we just keep repeating this process until we converge onto the bottommost layer. And the reason why this works is because the graphs at like the lower layers are actually more dense. So like there's whatever vector that you have on like the topmost layer, it will definitely be in the bottommost layer. So that's why we can keep doing this process. Yeah. So I think the paper over here. So this is this approximate nearest neighbor approach, and I think it uses like a few techniques to actually speed up nearest neighbor search, right? So I'll be going through like some of them. I'll be going through like the Panama as well as the SNP fast neighbor graphs that's parameterized by alpha. Okay, so first I think we should go through this to random neighborhood neighbors. So what this graph tackles is that it solves the approximate nearest neighbor in high dimensional spaces. So according to like the wiki over here, that KD trees, which is what we traditionally use to find like the nearest differences, actually performs quite poorly for high dimensional spaces. And what the paper proposes is that we can actually use randomized neighborhood graph. These are the time capacities of like RNG it takes quadratic time complexity and it also takes n log n memory. And it answers ANN queries in block 2n. So the naive approach would be ON because we go through every single vector and then we find, oh, what is the vector that has the least distance to query vector. So I'll try my best to explain how this works. So for my understanding of the paper, what we do is that so we call it the time complexity is n squared and n log n, right? So just keep these two metrics in your head when we go through the algorithm. So so for every point p, right? So for every point p, we have in like a high dimensional space, right? So let's say we pick a point p. Then what we do is that we try to extend a code on that point p. So this is the code that is extended by point p. And so there is some points that are covered by this code over here. And for every code that we actually extend on this p, what we do is we actually permute the points. So what does permute the points mean?
It's a little tricky, don't worry about it.
Yeah,
So
so
annotate, you just press the pencil button on the bottom.
so what does permuting the points mean? So permuting the point, this is where the random comes into play. So there should be a randomly permute the points. So what this means is that given this set of points, there are no numbers initially. So we're just going to randomly assign numbers to the points. Let's say this is 1, this is 2, all these numbers are randomly assigned. So after we have assigned the numbers to every point that is covered by the cone, then we will we'll start from 1, right? So an edge is added among the lowest distances. So we start from like the first point. So we start from 1. And then we realize, oh, there is no edge. There's no edge that's a lower distance. So we just draw an edge on P to 1. Next, we go to 2. We realize that, oh, there is already an edge that is lesser than, there's an edge that is already closer to P. So we ignore 2. We do not draw an edge between P and 2. Next, we go to 3. We realize that, oh, there is already an edge that is closer to P, which is this edge that we have drawn over here. So we repeat this process until we hit point 4. So when we hit point 4, oh, we realize that actually the distance between P and 4 is closer than the distance between P and 1. So that's why we draw an edge here. So this, I hope this sort of gives intuition as to like what this statement means. Yeah. And then you can repeat this process, and then eventually you'll end up with like this graph over here. So this is where the randomized neighborhood graph comes into play. So if you recall, it's n squared time and n log n memory. And the reason why it's n squared is because we are doing this for every point p, and then for every point p, so this the ON comes into play, and then we are doing this for every cone. So this cone is sort of like an ON as well. So n is actually an upper bound. Yeah. And then if we call the memory is n log n, why is it n log n? Because there's a proof that if we randomize this, we will extend to at most O log n points. I'm not exactly sure why it's log n, but now if you imagine if we do this for every point, that's why the memory is n log n. Yeah. This makes sense. So there is a lemma that I saw in the paper, which is there's some angular diameter alpha that's depending on like the Yisong. So essentially what this lemma is saying is that I can go back to the previous one. So what that lemma was saying is that we can actually toggle, because remember, like how do we know what is the angle of the cone, right? How do we determine the angle of the cone? Because the cone could be like this, and then it would spread a larger number of points. How do we determine the angle of the cone? And that actually comes from this diameter over here. This estimates like the diameter of the cone, or like the angular diameter of the cone. And what this is saying, right, is that the wider your cone, right? So the wider your diameter, the wider your cone, the less accurate your estimation will be. So to see why, maybe you can go back to the previous picture again. And then try to illustrate that why is it less accurate if we expand angular diameter of the cone. Yeah, so if now let's say right, we have more points here, and then if we extend like a cone over here such that the angular diameter of the cone is larger, right? Because we'll be repeating this entire process again across all these points and pick like a subset of points that is closest to the thing, right? As opposed to let's say if again we have P, and then if let's say like we restrict like the angular diameter to like super small, right? There's only like one edge that can be drawn to like that note, that point in the cone. That's why it's more accurate because we're covering more points. As opposed to like expanding the angular diameter of the cone. Then we can like extend to like a lesser number of points. So that's why it's like less accurate. Yeah. So this lemma, this is what like the lemma is saying. Yeah. Basically, the narrower your cone, the more accurate it is. The larger your cone, the less accurate it is. Because you can cover because the number of points that you're estimating is like larger. That makes sense. Okay, cool. And I guess like an optimization for like the RNG, the random neighborhood graph that I described earlier, actually it doesn't really perform well in practice. So to actually achieve practicality, what they do is that they perform pruning, like what Frederick has mentioned, right? So the idea of pruning is that we remove certain edges or remove at certain points. But of course, what is the trade-off? The trade-off is that the more edges we remove, right, we actually reduce the accuracy because this sort of like diminishes like the greedy definitely works guarantee, right? Because the points that we remove might potentially be like the answer to like certain query vectors that we are querying. Yeah, so I guess the heuristic or like the mitigation against this is that we can actually attempt to visit unvisited points. So after we have visited all the nodes like the SNG, the sparse neighborhood graphs, we can visit the unvisited points again. And I guess another heuristic that they use to improve is that they use a KD tree to choose a smarter starting point. Because I think there are different different starting points can affect like the accuracy of your answer. Maybe like let's say if you go back to this example again, like let's say this Q is my query vector. And on this presentation, it's easy to see that okay, 9 is the closest answer, right? 9 is definitely the thing. But the thing is that if we query for Q, we realize that okay, so because we only have like P6, we have P6, we have P4, and we only have P1 in our graph. We don't have P9 in our graph. So this will assume that okay, 1 is the closest point to Q. You won't see 9. So this is why it's an approximate algorithm. So after it goes to 1, what we will do is that because we are extending the edge for every point P. So again, for 1, we can extend, we could potentially extend to 5, to extend potentially to 2, right? And the thing is that Q will only see like the edges 5, 1, and 2. It will never see 9. Yeah. So this is like the downside of like the algorithm. This makes sense.
Guys following? Have any questions? Okay, great.
Yeah. I guess like the last part for my presentation is the Bamana indexing algorithm. So basically, this is essentially how alpha is basically like a parameter that we can fine tune, that we can adjust to actually to decide like, oh, how aggressively do we want to prune the number of edges. So Yeah, so you can see like the variance in the number of edges, the more we fine tune alpha. So this is another algorithm that they use to speed up the ANN algo. I think that's it for my presentation.
You guys need the. Well. That. Now, why don't we take a 2-minute break? 3-minute break? Well, hopefully all of you have organized in groups already for your project. I've been making comments on most of the group projects, so for ideation, there's not that. You just want to make sure that you have budgeted a right amount of time. Again, early in the semester is usually better for students, so you can front load as much of your project as you manage. Okay? Because I mean, your lecturing and support duties are pretty much uniform throughout the semester. But then your project work is not. Certainly your other courses are not. You will also, for each of your projects, you've got the project number opening from me in your Slack thread. So once you have your number, you can go back to the sheet, the Google sheet, and then change your project number or team ID there. Okay? There's a column for that towards the left side of things, like column B or something. A separate thing I might want to say that from PhD students, you're thinking about topics and quantization. Those are great topics because when you do data reduction, it makes it easier to scale up. So you have more compute to do, less things, more items. So that's and like all of us have talked about with quantization, it does work very well in parallel. So I also wrote on the general channel. There's good documentation, mice, basically AI search, approximate search, similarity stuff. If you understand that those set of algorithms well, I think we're in pretty good shape. I mean, I don't think that many people outside of industry will apply it. So having that sort of understandable would probably help you in your. Yeah, so I thought when you read.
Yes, I guess I'll start now. So in the previous few sections, our previous few presenters have given
very in-depth breakdown of the important algorithms for vector retrieval and different methods of effective vector storage. Yeah. So like from now onwards, the rest of our presentations will be a bit lighter, focusing less on the vector databases and more on the process of like retrieval augmented generation and how we can tackle challenges related to rank. Yeah. So today I'm going to talk about speed and rank. Yeah. So yeah. So what do I do with my rank pipelines? Right? This is a question that perhaps a lot of people in the industry ask. So there are multiple things that when people come at it from different angles. So one thing you can do is make algorithmic improvements to a vector search. So for example, like the previous few algorithms that like the presenters have talked about, these are all improvements over the years to the algorithms. And as such, I'll not talk. Yeah. A second improvement is process to vector retrieval and re-ranking. So we have a week which is dedicated to retrieval and re-ranking, that is week 6. So I will not talk about these process improvements as well, but to like but terms like adaptive retrieval or speculative retrieval, these are all things that you can do to speed up the rank timeline in that end. So given that these two are not going to be talked about today, what is left, right, is so-called process vectors. Yeah. So I refrain from going too deep. For example, storage optimization and like the hardware details. So I will cover some lighter stuff, but these are some things that people have done to give an overview. So for example, there's like a FPGA as a vector search, and also GPU-based resource optimization, where like you separate the retrieval corpus into hot and cold clusters. So clusters of documents which are more frequently retrieved and clusters of documents which are less frequently retrieved, and you store some in the GPU and store the less frequently retrieved ones in the CPU, so that the GPUs can calculate the similarity search faster, thus speed up the rank time. And the one that I'm going to be talking about today is KB cache reviews. Slide. Just to make sure everyone is on the same page, that everyone know what a KB cache is and how it works. Okay, so let me just go through it. In transformers, right? Like you know, the LLMs do next token generation. So each new token depends on all the previous tokens, especially in the attention mechanism. When you are trying to generate the next token, you try to look at how it relates to all the previous tokens. So you need the key and the value representations of every earlier token to generate the next one. So as a result, you can tell that there is going to be some sort of repeated computation every single token in a sentence. So to avoid this recomputation, we will store the past K and P values of the previous tokens in a cache, so that every time you have a new token, you only need to calculate that new token's K and P value. Yeah. Okay. So the main point is that like the KB cache will help you to compute less tokens, less things every token. Yeah. So in this paper, the whole rank, like the problem setting that I identified is that the repeated recalling of different document chunks like will generate repeated KB cache computation. send your LLM a series of queries and the same documents keep getting then you will have to keep recomputing the same key and value word key and value yeah, and that is very expensive. Yeah, and over augmenting your query with all the chunks of text that you pull from your database is also very expensive. Yeah. So the idea is that you can recompute and store the KV cache for each document in the database. And then during generation, all you have to do is to simply concatenate KV cache for similar documents. Yeah. So over here, right? Instead of having a really long form, all they take the KV cache for documents during retrieval, and then afterwards then concatenate. Then you add programming. Yeah. So does anyone have any questions about how this looks like in practice? Anything that seems out of the ordinary? Like maybe something is missing, right?
How is the KV cache kind of different from the documents that we are fetching from the RAG? Is it like vector embeddings or something?
Yes, it is embedding of the yes. You treat your document with the embedding code, then you come up with a bunch of embeddings that you can use to generate next tokens. Yeah. But I guess the point that I was trying to be is that when you concatenate your KV caches like that, over here, right? The documents no longer pay attention. So for example, when you send it all in a very long query, then the attention mechanism sometimes will make the words in one document pay attention to words from the previous document. But we don't have that anymore if you compute the KV cache in it. Yeah. So the authors also treated this. My next slide. Yeah. So the point that the authors made was that the cross-document attention is sparse. So as you can see in the attention map over here, sometimes in this area, this is, for example, different documents being attention. Sometimes there is attention being paid between them, but mostly it's sparse. So they suggested that we can just take it out and then apply. So in fact, this applies some sort of master attention between documents. And with appropriate fine-tuning, the LLMs can still adjust this and achieve good results. Yeah. Yeah, so another thing that authors have treated is that after you concatenate the KV caches, you also have to treat the positional encodings of the tokens. Because if you just put the KV caches in a composite manner, then each KV cache will use the original position ID search. And if you do some sort of reordering, so in a sense rearranging the position ID for tokens in each chunk to be in monotonic figure, then there's some sort of notion of order between the KV cache tokens. So the LLM will know that this is from the document and later and this is from the document. Yeah. And the performance shows that it does help, having some sort of notion of relative order preserved inside the position helps the rank pipeline perform better. But in all cases, the most important part of this paper is the speed up. So for example, it of all these long bench document, which is basically like a long contents bench. Yeah, they perform at a similar platform as naive rank and also at 9 times speed. Yeah. Okay, so that is one simple idea that you can do. Increase your speed of the rank even without helping, for example, the needle part. So next I'm going to talk about effectiveness. So that is on the question of what to solve. So this paper is focusing on a particular problem setting of recursive summarization. So as you know, current rank methods usually fetch short and contiguous chunks of text. If you have a really long document, they won't fetch everything in. They only fetch like a certain chunk. Yeah. So that is good for recalling facts, but it may miss like the large scale theme in a certain document. So for example, if you want to summarize a story or ask questions about the theme of the story, it's really difficult for the rank to give an accurate answer. Yeah, so for example, in this benchmark called narrative QA, they ask questions about stories. And like certain questions require information across the entire story. So you need some sort of summarization. And the authors here draw a line of research on recursive summarization. Okay, so this paper's implementation of recursive summarization is in sort of recursive clustering. So how they do it is that firstly, you break all your text in your retrieval corpus into maybe 100 chunks, just as you. And then afterwards, like we'll cluster them by their similarity. So chunks that are talking about similar things are clustered together, and then afterwards, they will be summarized by an LLM. Doesn't have to be a really good LLM, it can just be a cheap LLM. So for example, in this paper, the authors use like GPT triple Python. Yeah. And then afterwards, if after the summarization, the length of the summary by the LLM is still too long, then you can recursively do the same process. Yeah. And as a result, you will build a tree with root layers. Yeah, and in the contents of the node, you will have text embedding, and also text being summary, and also links to the child nodes, and also anything. Okay, so the authors here, they explored different methods of retrieval, because after obtaining this recursive like a data structure with like I guess nodes containing very high level information and very low level information. How are you going to converse it, right? They explored two methods. So one way is tree traversal, and another way is collapse tree. So as always, you have a query, and then afterwards, then you encode it, and then you have an embedding, and then afterwards, you try and do similarity search, right, between your query embedding and your document. So in the tree traversal, like they will retrieve the top k nodes at every level. So you are going to have an equal number of high level nodes and an equal number of low level. And in collapse tree retrieval, you are just going to collapse the tree. So like you don't impose any sort of restriction on like the quota of the number of nodes that you take from every level. You are just going to take like the k most similar nodes in them. So it's going to be like a mixture of high level nodes and low level nodes as well. But perhaps this is more flexible, because if your question is asking something which is more on the lines of details, then you will want to retrieve more low level nodes and vice versa. Yeah. So these are different ways that they explore trying to traverse the tree, and like due to flexibility, the collapse tree retrieval is better than certain other things. Yeah. So these are some of the interesting ideas that like I have found from reading papers on how to accelerate, correct, and also use it more effectively. That's all.
Questions for Kaita? Yeah, we're running. And so.
I actually found it because I was searching one of the regarding guys online there as well. Okay. That's good. So let's introduce any techniques about efficiency, and I think memory is closely related to efficiency. I'm going to take more deeper dive into embeddings in action with efficiency. So has anybody encountered this error? Is raise your hand? We are running out of code. Basically everybody in this room. So how to address that? Any answers?
Smaller model.
A smaller model.
I more memory.
Okay. 5 more memory. Okay. Yeah, I think it's very clever joke from good old Python that says OOM error is 5 more memory. Very clever. Okay. So so here's basically the a very abstract realization about how this works. To documents, okay, and then we pass it the collection documents into your network, produces documents embeddings, and in the inference time we call the query to select match these embeddings. How about we take a closer look? So how one document represented? So I think here is a high-level abstraction of the aspect sentence word that we use an encoder to encode the document, right? So we have this array of tokens passed by this transformers model of self-attention, and layer by layer. We can see that it's super memory intensive because every token has its own embedding. Every layer has its multi-layer perceptron and self-attention by 12 or 18 layers is super deep and how to press. So our physics of the talk is that we want to diagnose what is the capacity of embedding informed by this scientific question. We can then design like a question algorithm. But let me give you guys one thing. So this is my favorite paper from ENLP. I think many of you were there because it's a local conference. So this paper is an outstanding paper by John Morris, who is a hot taker on Twitter. So basically, the takeaway from this paper is that sentence embedding can be used to recover the sentence almost exactly. So this is the takeaway, which means that sentence embedding, like the 768 dimensional embedding, means that sentence exactly. How they do so is that they first have the proper embedding, then they do such unembed, denoted by this small yellow function, and got this and unembed into a string of text. Then we embedded again to another data representation. Then we do it iteratively. Finally, the embedding will be by the original packet embedding. And the byproduct is that this way, the text in the sentence embedding
almost correctly. So the takeaway is that sentence embedding means the sentence. Here's the second thing. So here's the neural network transformers attention map for how the sequence is being processed. We can see that in the first two layers, denoted by layer 0 and layer 1, you see that the attention is pretty localized. We can see that in the diagonal line, you see they're repeated. But when the layers move upward, in the layer 2, layer 9, layer 16, and so on, see that it's not quite localized. Everything will look at the beginning of the sequence, meaning that everything will just look at first one. Then we call this type of behavior to sync to the current transformer models. So informed by this, I'm going to move Mr. Bishop away. Sorry. Informed by this behavior, the author of the paper, they innovated a new algorithm called string LLM, meaning that we don't need the full attention. We only need the local things, and here in the first one. So here we have two things. The first thing, why embedding? Please, sir.
Actually,
Yeah.
why do attention sinks appear? Is it because like keep compressing?
It's a good question, and I think I would recommend some review of which is the work package. This year's phone companies. So I think they have a paper of why attention happens. And perhaps okay, scan. Yeah, but I mean, for the interest of time, perhaps we have to skip here's a to yes, so you can check this guy. Something is my page, my app, so Facebook. Right. Okay. So we have two things. Why embeddings? First thing. Why embedding? First token. Are you getting it? Yeah, we can just use the first token as one embedding to represent entire documents. And this informs the method of XWrap that we're going to present today, which is a paper at Eric's last year. So I think from the figure one of the paper is very apparent what they're doing. So let's read the figure for 20 seconds. Everybody can get it.
Get a comment on the graph.
No, I don't think. Okay. And so 20 seconds passed. I think everybody knows what's going on, but still, let me paraphrase. So here's the vanilla version. We have a question and the model unfortunately got it incorrect. And this is the vanilla drag version. We have a very long background, which is very memory intensive, and it's a correct answer. And for the paper extract, use the first token, this first one token, as an extreme express of the long code. Then model just got it correct. So their work's contribution is investigate how to represent this guy. This one, right? So can anyone help us think about what would be the challenge of directly using document and graph? What would be the challenge for that? What would be the challenge? Any big guess? Just use the document. Is anyone have a guess? Efficiency. Right. So, but we are already using that. That's one document, right? Like that. What would be the challenge? And that's the efficiency has to address. And what other components will the document have?
It's like when you say doc embedding, do you mean you just put the embedding inside the prompt instead of the
I think the document will be just like this.
so it's a series of numbers.
Right. Or just one embedding. Short combinations.
Then the question is how the LLM will be able to understand it.
Yeah, exactly. I think it is very close to the answer. The answer is modality mismatch. Because in the graph of the data store, their primary features or usage is for retrieval. So the sentence embeddings are optimized for retrieval for the similarities. However, for the downstream language model, their objective is to generate. So it's a general purpose model, not a specifically retrieval model. So here's modality mismatch. So the contribution of this work is primarily here, this prior technology. This objective, they keep everything else unchanged. Everything else is the same. The vector store is unchanged. The model is frozen. The only thing that's being changed is vector. And is that they take the sentence document embeddings out and they project the embeddings to the common space of the language model so that the language model can use the embedding for the task. Okay, so they have devised the two objectives for learning such projection. The first objective is called paraphrase pre-training. They take inspiration from the vision societies called BERT, because they want to align the two modalities, image and text. So they do something similar, like they are going to caption this embedded into the document. It's pretty much similar to Murray's email characteristic. And the second objective is really using embedding. So they take this embedding and do a battery of instruction training, like downstream summarizations and open domain systems. So idea is that we have this embedding, but we have to use it very well. So to do so, they try to fit the AL distribution to RAG and abstract distributions. Okay, so we don't have to go through the compare results because it's very good. Otherwise, the paper won't go to yours, and we only have to look at the analysis result. So the authors have devised the two new metrics. First is called resilience, meaning that we don't want the actual context to fool the model, meaning that before it's correct, after the RAG is still correct. See that an XRAG is pretty robust compared to the vanilla RAG baseline. Anyone sharing says why XRAG is robust? For the interest time answer, I think the answer is that XRAG has a sort of denoise because during the instruction activity stage, such one small embedding has been learned to fit with the internal knowledge of LLM, and there is still fewer noises compared to the vanilla retrieval contents. Secondly, there's another method called boosting. Boosting is that beforehand, without the context, it's incorrect, but with the context, it's correct. So according to this figure, can anyone tell us which data set is most challenging to extract? From this figure alone, which data set is most challenging? The third one, right? Yes. So top 30 is the most challenging. So why do you think top 30 is challenging?
Those are both like
multi-pop from different parts of the text. Excellent. So what's my next? Inverting. Yeah, Grace. So it's a plastic answer from Indra. So the answer is that Grace is a multi-purpose data set, and meaning that such single embedding is due to the end to surface such hierarchy or language structure might stand out in such embedding. Pretty much for me. Any questions? Thanks.
Let's thank our speaker. Get a box, so we'll go directly to our last presenter. Function.
It's gonna be really, really related. Yeah. Although we cover all the really like heavy technical stuff, your search for your. So now we'll take a look at we'll just take a look at what's there, right? Commercial vector databases and open source databases, right? So good chance when you want to like implement like something, they're not going to be like writing out your like search functions and your data. It's going to be down to like what databases they are and what they want. So maybe you want to take a look like the search performance, like mentioned before, like the recall and the latency, and how much can the load capacity, right? How much can you query at once? How many dimensions your vectors can query it? And are there certain features that certain databases have and others don't? And whether they can support GPU and FPGA support that mentioned before. It's one of the optimization strategies. So so for a select number of these vector databases, most of them will support your popular indexing methods, and as well as for scalability concerns and also replication sharding and partition. So if you have any like specific distance function, you have any specific indexing methods one, so that's one thing you have to look out for, right? Whether your database caters whether it can support that, right? So one of the more important things is the performance. So when tested on 3 different data sets, right? So you see for these vector databases, there's no one database that is like really good at like all the metrics, right? There's trade-offs, some perform better than others. And then so I suppose it's just down to like what's your use case, right? I think one of the few the question catalyst was like if you need something with like really, really like high recall and low latency, then yeah, so you'll take your pick from here, right? So that was like the more technical part. This is a bit more like database stuff. So these are also things you should consider whether your database can support this, right? If what happens if you suddenly have 10x users or your data gets really, really big, right? So these are the more like ops side of things. So for open source, these are some of the more popular and like well-known ones. So this is just a really fun like so apparently like Barid is like the in-memory database. It could also be used for vector storage, and apparently it's like really, really fast. So that's a notable mention. So for a lot of the open source databases that you can find, they also like do come with like a company like cloud services. So that's like one thing you could consider. So if like you want to do fast prototyping, you want to do like fast prototyping, you could like you pick any one of these, and eventually if your users you get a lot of users, right, your demand gets a lot more, right? Just buy into like the market. So yeah. So it really depends like what you need, what your use cases are, and how you take them, right? Whether it's you need healthcare finance or you need like enterprise level stuff, right? So you go with the phone stuff. Okay, this is something. Okay, thank you.
I think questions for back then. I typed it, sorry. final one? If not, I think, yeah, it's ready to state, so we'll end class here, so thanks for coming today. Next week we are going on to, fine tuning and back to LLM work. Alright, so thanks for setting all the stuff up today. If you want more details on your projects, again, just mention me, I'll try to get to this Friday a little bit more. Alright, so thanks very much.